Before we delve in more detail into acid-base reactions, it's important to remind ourselves that these acid-base reactions control a delicate balance in all living organisms. They control the uptake of carbon dioxide from the atmosphere to the ocean, thereby controlling climate, where the carbon dioxide is increasingly produced by fossil fuel combustion. But acid-base reactions also play a major role in pharmaceuticals and in the new technology of battery development. And finally, acid-base reactions are very important for the creation of new photovoltaic structures that convert sunlight to electricity. So let's take a look at three overbearing themes that have emerged at this point. The first one is that acid-base reactions release free energy as they progress from their initial condition to their state of equilibrium. And that, of course, emerges from the fact that they're spontaneous. But a major contribution to the release of free energy is a single important reaction, and that's the reaction of H3O plus the hydroxide anion that together react to produce water. And as we will see, the release of free energy from that single reaction, an acid reacting with a base, is a primary driver in acid-base reactions. Now, the second aspect that we want to remind ourselves of is that if we look at the dissociation constant for an acid, and then we consider the base dissociation constant for its conjugate base, and it's very important to realize that this is an acid conjugate base pair. In that circumstance, we can write that the product of the acid equilibrium constant times the base equilibrium constant is identically equal to the equilibrium constant for water. And of course, as we know, at standard temperature, that's equal to 1 times 10 to the minus 14. The third thing is that when an acid and a base are added to aqueous solution, there's this overwhelming tendency to form water. And this is identical to what we mentioned before in the release of free energy, because when I write that reaction of H3O plus and OH minus forming two water molecules, it's important to realize that the equilibrium constant for this reaction is exactly the inverse of the equilibrium constant for the dissociation of water. That means that I have 1 over 1 times 10 to the minus 14, and that's equal to 1 times 10 to the plus 14. That's a huge number. This is a very large equilibrium constant. So at equilibrium, when I calculate the release of Gibbs free energy under standard conditions, we know that that's equal to minus RT log equilibrium constant. That's equal to minus 79.9 kilojoules per mole. That is a very large release of Gibbs free energy. So the analysis of solutions involving the addition of an acid and a base are termed neutralization reactions. That's a very important class of reactions because these neutralization reactions are driven by the release of free energy from this very same reaction, H3O plus OH minus, going to form water. And the technique for handling these neutralization reactions is to first analyze the strengths of the acids and the bases involved. And we define in this process 4 categories. The first category we want to look at is a strong acid added to a strong base. This is a very important class. The second class we want to look at is when we add a strong acid to a weak base. And as we'll see, we treat these in very, very different ways because they interact very differently. The third category is when we add a strong base to a weak acid. And in this case, there's a great similarity between category 2 and 3. And finally, when we add a weak base to a weak acid, we've completed all the categories that we need to analyze acid-base reactions.